we got initiated into parabola in the last class. If I recall right, towards the end of my last class, I gave you a crasher on polynomials, a relationship that connects the roots and coefficients of a polynomial, some of the roots, some of the products taken two at a time, etc., and so on and so forth. Remember that? Did I discuss with you some basic stuff about focal chords, tangents drawn at the extremities of a focal chord, perpendicular, and that they meet on the directrix? And conversely, if you take any point on the directrix and draw a pair of tangents to the parabola, they would be perpendicular, and the chord of contact would be a focal chord, right? For a standard parabola, y squared equal to 4ax. If t1 and t2 are parameters at the extremities of a focal chord, then t1 into t2 is -1, right? So some of these properties, some of these facts, we got familiar with as a basic understanding of parabola. Let me continue with some more stuff, very related, pertinent stuff. We'll deploy the standard parabola to understand those properties. Y squared equal to 4ax. So if this is a parabola, standard parabola, y squared equal to 4ax, and if I have any point P on the parabola, call it at squared comma 2at, right? T is different for different points on the parabola. This is the parametric representation of points on the parabola. This is a tangent at T. We call it a tangent at T. We refer to this point as T. The moment I say T, we translate it into at squared comma 2at. But I'll call this point T for convenience, right? So this is tangent at, so to say, T. And the equation of this tangent, if you remember, is yt is x plus at squared. The slope of this tangent, therefore, would be 1 by t. In fact, we could have said x is at squared, y is 2at. One way to obtain the slope of the tangent would be to say dy dx, which is equivalent to saying dy dt divided by dx dt out of chain rule considerations, right? Which is like dy dt is 2a and dx dt is 2at. That's another way you could have obtained the slope of the tangent at any t, which is 1 by t. The slope of the normal is a line passing through the point of tangency and perpendicular to the tangent. That's a normal, right? That's a normal. So a line passing through the point of tangency and perpendicular to the tangent is a normal, This is a normal at T. So we say T is the foot of this normal. We say T is the foot of this normal. T is the foot of this normal. That's what we say, right? Now, since this is perpendicular to the tangent, if the slope of the tangent is 1 by t, what would be the slope of the normal? Minus t. Slope of the normal, therefore, is going to be minus t. Now, this gives us ample opportunity to obtain the equation of the normal. I know a point on the normal. I know the slope of the normal at t, right? So we can find the equation of the normal at t. So the equation of the normal at t is given by y minus 2at is minus t into x minus at squared. How about it? Yes or no? Right? This normal intersects the axis as at G. If this is the axis of the parabola, then the point where the normal intersects the axis is G, is commonly referred to as G. In this case, axis is y equal to 0. The x-axis is the axis for a standard parabola. So if you plug in y equal to 0, you get the x coordinate of G. For g, y is 0. If you plug in y equal to 0 in the equation of the normal, you get the x coordinate of g. Yes or no? So plug in y equal to 0. X is then 2a plus at squared would be x of g. 2a plus at squared would be x of g. The point where it intersects the normal. Right? Now, can I just remove the clutter from here? And one more thing, the point where the tangent intersects the axis is t, is commonly referred to as t. This is the point where the tangent intersects the axis. So in this, if you plug in y equal to 0, you get x equal to minus at squared, x equal to minus at squared. So the point where the tangent intersects the axis is x is minus at squared, y is 0. X is minus at squared, y is 0. That's where the tangent intersects the axis. Yes or no? Right? And in fact, where is the focus? The focus is S, A0. Right? G is the point where the normal intersects the axis. T is the point where the tangent at the same point intersects the axis. Right? Do you observe clearly from here one basic fact that S is the midpoint of TG? Check that out, please. This point T is minus at squared comma 0. This point G where the normal intersects is 2a plus at squared comma 0. The focus S is A0. Do you realize that this is the midpoint? Right? This plus this by 2 is this. 0 plus 0 by 2 is this. Right? So the focus is halfway between the point where the tangent intersects the axis and the normal intersects the axis. That's where the focus is. Right? Focus is the midpoint of TG. Clear? Now, wipe this off. Okay. So what we arrived at is the following. Let's say if this was a standard parabola, call it y squared equal to 4ax. If this was a standard parabola, call it y squared equal to 4ax. And this is a normal at a point P referred to as T, whose coordinates therefore are rendered at squared comma 2at. Then the slope of this normal is minus t. The slope of this normal is minus t. The equation of the normal at t is y minus 2at is minus t into x minus at squared. Now, like I told you, this is called the foot of the normal at t. This is the foot of the normal. This normal, suppose it passes through a point Q. Suppose this normal passes through a point Q, which is h comma k. This normal passes through a point Q, which is h comma k. This is the equation of the normal, and let's say it passes through a certain point Q, which is h comma k. Then h comma k will satisfy this equation. X equal to h, y equal to k will lie on the equation of the normal, will therefore satisfy this equation. Yes or no? Yes, right? Which means k minus 2at is minus t into h minus at squared. Yes or no? Right? Which means what is t? T therefore should be looked upon as the foot of the normal drawn from a certain point Q to the parabola How should we interpret this? We should interpret it as follows. P or T, the point T, is the foot of the normal from a point HK to the parabola? Yes or no? I could have looked upon T as the foot of the normal from a point HK to the parabola? Yes or no? That's the way we could have looked at T. Foot of the normal from Q to the parabola. Q HK to the parabola, right? If I solve for a given HK, if I solve for T, I'll get the foot of the normal from HK to the parabola. The number of values of T that will emerge out of solving this will give me the number of feet of normals that could be drawn from Q to the parabola. Yes or no? Yes or no? Each T will represent one normal. Normal at one T. Now, very clearly, this is a cubic in T. Let me coagulate terms here, put them all together and solve for T. At least pretend to solve for T. Okay? AT cubed plus T into 2A minus H minus K is 0. Which is what? A cubic in T. See? AT cube plus T into 2A minus H minus K is 0. Is a cubic in T. Giving me 3 values of T. A polynomial of degree n in general will give me n values. Right? We'll have n roots. This is a polynomial of degree 3. In general, it's going to produce 3 values of T. Real or complex, distinct or coincident. That's another issue. But 3 to be precise. Okay? Which means from a point HK, each T will give me 1 foot of the normal. 3 T's will give me 3 feet. That means 3 normals drawn from HK to a parabola. Yes or no? So in a very general sense, in a very generic sense, 3 normals could be drawn from a point HK to a parabola. In general, 3 normals could be drawn from a point HK to a parabola. Yes or no? Right? You know what I'm saying? And they could have been looked upon as follows. Given a point, given any point Q, say H comma K, in general, one could have drawn a normal at T equal to T1, at T equal to T2, at T equal to T3. From a point HK, normals could be drawn at T equal to T1, at T equal to T2 and T equal to T3, where T1, T2, T3 are the roots of this cubic in T. Yes or no? T1, T2, T3 will be obtained by solving for T. Yes or no? Right? So, this cubic has roots. T1, T2, T3. These are the feet of the 3 normals drawn from HK to the parabola. That means in general 3 normals could be drawn from any point to the parabola. It's not like all the 3 normals would have to be real, right? We'll come to that discussion later on, but in a general sense 3 normals could be drawn from a point HK to a parabola. Clear? Where T1, T2, T3 would be the roots of this cubic in T. Clear? Now so we have from a point Q, normal drawn at A, which is T equal to T1. That means this point has coordinates AT1 squared comma 2AT1. A point B with parameter T2, its coordinates would be AT2 squared comma 2AT2, and a point C, this point AT3 squared comma 2AT3. right? So A, B, C are the feet of the three normals that could be drawn from HK to the parabola. What it means is, at A, if I draw a tangent, that will be perpendicular to QA. At B, if I draw a tangent, then that tangent will be perpendicular to QB, and same for C, right? That's what it really means. Now, these 3 points are special points on the parabola. These 3 points are special points on the parabola. If a normal is drawn at A, and a normal is drawn at B, and a normal is drawn at C, then the 3 normals seem to be concurrent lines. They intersect at Q. Yes or no? That's the way we could look at it. That means normals at A, B, C are concurrent lines. Normals at A, B, C are concurrent lines. Thank you. Give me some time here. Even before I finish completing the discussion, you know, yes, that's what I'm arriving at. I'm just saying properties of the 3 such points. I never said these are 3 unique points, right? If you change HK, if you change the position of Q, you get different sets of T1, T2, T3. A third HK, you get another set of T1, T2, T3, isn't it? That means for any HK, you will have different triplets of ABC, isn't it? Is that what you're asking? No, for one H comma K, there will be only one set of 3 points ABC, because you'll get only 3 roots, T1, T2, T3. For a given HK, you'll get only 3 roots of this cubic. But they are not normals. They are extremely abnormal.
But then you can make a line perpendicular to them, right?
But will that be a tangent to the parabola? Right. Got me now? So, normals at ABC, these are 3 special points having the property that tangents, that normals at these points are a bunch of concurrent lines. These normals at ABC, if they are concurrent, then these 3 points are referred to as co-normal points. These points ABC are referred to as co-normal points. ABC then are referred to as co-normal points. Right? Not every set of 3 points on the parabola. It's not like if you select any 3 points on the parabola and you draw normals at ABC, then those normals will intersect at the same point. Right? So there would be special points, special sets of 3 points that will enjoy this property. Right? There will be special sets of 3 points that will enjoy this property, and every time 3 such points on the parabola enjoy this property, then these points would be referred to as co-normal points. Clear? And any point
No, on the parabola
huh?
can be a part of the set.
Yes, 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 yes. Of course, of course. No, 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 no. Don't jump to that conclusion. That's going to get bizarre. No, I never said. I'm not talking about normals from inside and outside, right? That's outside the scope right now and beyond your understanding. But trust me, it is not about inside and outside of the parabola, right? It's all the same when it comes to normal. Right? So, now, talk of 3 co-normal points. Talk of 3 co-normal points ABC. Right? So, if these are 3 co-normal points ABC, with feet being T1, T2, T3, then the normals at these points intersect at H comma K. Right? And the 3 T's are roots of this cubic. For a standard parabola, are roots of this cubic. Right? This one will have slope minus T1. This normal will have slope minus T2. This slope will have slope. This normal will have slope minus T3. Slope at T, slope of the normal at any T is minus T, isn't it? So slope of the normal at T1 would be minus T1, minus T2, minus T3. Yes or no? Now, the coordinates of A, what are those? A T1 squared comma 2a t1. Coordinates of B, a t2 squared comma 2a t2. A t3 squared comma 2a t3. Right? These are the feet of the three normals drawn from hk to the parabola, roots of this. Now, this is like at cubed. This cubic is like at cubed plus 0 into t squared plus something into t plus something equal to 0 is this cubic, right? Yes or no? Right? With roots t1, t2, t3. Now from the last part of the discussion that we had previous class, the sum of the roots of a polynomial, would be minus the coefficient of the second highest power divided by coefficient of the highest power, right? So t1 plus t2 plus t3 would be minus 0 by a. So that's going to be 0. That's going to be 0. Yes or no? Right? That's one property of three conormal points. Prince. If t1, t2, t3 are the roots of this, then sum of the roots would be minus the coefficient of t squared divided by coefficient of t cubed, which is what we discussed in the last class. So you should have remembered that. No. Come prepared with what I do in the last class, otherwise you will feel lost, right? Minus coefficient of t squared divided by coefficient of t cubed minus the coefficient of second highest power divided by coefficient of the highest power, right? So that's 0, right? Sum of the product taken 2 at a time, t1 t2 plus t2 t3 plus t3 t1. Sum of the product taken 2 at a time would be minus 1 squared, first of all, into, after t squared, the next is t. What's the coefficient of t? 2a minus h divided by a. Right? And t1, t2, t3. t1, t2, t3. The product of the roots of the polynomial. 3 roots means minus 1 cube minus k divided by a. Minus k divided by a. Which is like k by a. Yes or no? Right? Now, can I just remove this for the time being? This at cube plus t into 2a minus h minus k equal to 0, like I told you, has roots t1, t2, t3, where t1 plus t2 plus t3 is 0. t1, t2, sum of the product taken 2 at a time is 2a minus h by a, and product of the roots, sum of the product taken all at a time, turns out to be k by a, right? Yes or no? Now, minus 1 cubed into constant term by a. See, when you come to the class, you know what I am going to do. You must certainly read up what I did in the last class, because it's a ladder-like phenomena. It's going to be connected to the previous rung of the ladder. Alright, so it was not without reason that I taught you this relationship between roots and coefficients of a polynomial. Now, if t1 plus t2 plus t3 is 0, then 2a t1 plus t2 plus t3 by 3 is 0, yes or no? Can I then say ya plus yb plus yc by 3 must be 0? Can I say this? y of A is 2a T1, y of B is 2a T2, y of C is 2a T3. That divided by 3 is 0? Yes or no? But what does this represent? Y of the centroid of triangle ABC. This represents y of the centroid of triangle ABC. Yes or no? Yes, so this was the triangle ABC. Where what were ABC? ABC were 3 conormal points. Not just any arbitrary set of 3 points. These are 3 conormal points. And a triangle, this is ABC is a triangle formed out of 3 conormal points. ABC is a triangle formed out of 3 conormal points. And as it turns out, if G is the centroid of this triangle, if G is the centroid of the triangle formed out of 3 conormal points, then the y of the centroid formed out of 3 conormal points is 0. Now, the physicality must be understood. This was a standard parabola. What is yg equal to 0? That means G, the centroid of ABC, lies on the x-axis. The centroid of ABC lies on the x-axis, yes or no? Right? On the x-axis means the axis of the parabola. X-axis means this is the axis of the parabola. So write down. The centroid of the triangle, constituted by 3 conormal points, must lie on the axis of the parabola. That's the physicality. Right? And the axis need not always be the x-axis. It could be anything. Right? The axis of symmetry, that is. The centroid of the triangle formed out of 3 conormal points must always lie on the axis of the parabola, no matter what the axis. Axis means the axis of symmetry. It may be the x-axis, the y-axis, or some line lx plus my plus n equal to 0. Does not matter. Right? Now, so that's an important property. Now, what? Not necessarily. No, not necessarily. That means ABC will be conormal points. That's not a guarantee. Because if T1 plus T2 plus T3 is 0, that would not mean that this plus this would be 2a minus h by a. That will not. See, if you said, I select any 3 points, right? And I find that the centroid of these points is G. Then all that it means is ya plus yb plus yc is 0. That means only this condition is met. But what's the guarantee that these conditions will also be met? Right? So it's not like every 3 points, the triangle of which has its centroid on the x-axis must be, on the axis must be conormal points. That's not guaranteed. Right? That only guarantees this condition. If this and this are also guaranteed, then the points T1, T2, T3 would be conormal points. You know what I'm saying? Yes. Right? Now, if there is a point P, call it T1. If there is a point P, call it T1. That means this point P has coordinates a T1 squared comma 2a T1. Right? And I draw a normal at P. Normal at T1. And I draw a normal at T1. Right? If I draw a normal at T1, then this point Q is the other end of the normal. Q is the other end of the normal. And this line need not be a normal at Q. If it's a normal at P, doesn't mean it's going to be a normal at Q. Right? So this is just the other end of the normal drawn at T1. Right? Say the other end of the normal drawn at T1 is T2. That means Q is a t2 squared comma 2a t2. A normal is drawn at t1 and t2 is the other end of the normal drawn at t1, right? Now if it's a normal drawn at t1, what would be the slope of this normal? Minus t1, not minus t2, minus t1. It's a normal at t1, right? The normal could also have been written, the slope could have been written in terms of t1 and t2. How? The slope could have been written as 2a t1 minus t2 divided by a t1 squared minus t2 squared. Yes or no? And that must be minus t1. Slope of PQ is y2 minus y1 divided by x2 minus x1, which is this. And that must be minus t1 because it's a normal at t1. So its slope must be minus t1, yes or no? Yes, sir. Right. So this must be equal to minus t1, yes or no? Yes, sir. Right. Which gives us 2 by t1 plus t2 is minus t1. Right? And this gives me t1 plus t2 is minus 2 by t1. And this gives me t2. Objective was given t1, find t2. Right? t2 then turns out to be minus t1 minus 2 by t1. t2 then turns out to be minus t1 minus 2 by t1. Yes or no? Which means if a normal is drawn at t1 to a standard parabola, then the t of the other end, which is t2, is minus t1 minus 2 by t1, where t2 is the other end of the normal drawn at t1. This is an extremely important relationship. Extremely important relationship. Hmm? Can I wipe this off? Hmm? No, then if the normal is a focal chord, then it's not. No, the normal is a focal chord means like this. You're saying this PQ. If the normal passes through the focus, yeah. So no, of course not. Certainly not. I mean, how can they be mirror images? See, focal chord means you are talking of, if they have to be mirror images, they have to be perpendicular. P and PQ must be perpendicular to the axis. But do you realize this is the tangent here? Is it perpendicular to this? This is a tangent here. Is this a normal anymore? The latest rectum, is that a normal? No. In fact, the only normal which is vertical is this, which is horizontal is this. There is no normal which is vertical. There is no normal which is vertical on this parabola. So if you think of this as a normal, then the tangent should have been horizontal. But you don't find horizontal tangents on the parabola except at infinity. When it's flattening out, except at infinity, you won't find horizontal, isn't it? If the normal is vertical, as is PQ, if you want P and Q to be mirror images of each other, then the tangent at P must have been horizontal. Now, see, for the tangent to be horizontal, the slope of the tangent 1 by t must be 0. So t must be infinity, isn't it? So that's not possible. Got me? So it's not possible. Now, suppose we have 2 points on the parabola. A which is T1, B which is T2. A which is T1, B which is T2, right? And say they have the following property, I draw a normal at B. This is a normal at B. This is a normal at T2. And draw a normal at A. I draw a normal at T1, that is. Right? And I find that the normals at 2 points of the parabola, they happen to intersect on the parabola. Suppose they intersect at C on the parabola. So there are two special points on the parabola. A normal I have a point A and I have a point B. And I draw a normal at A and I draw a normal at B. And I find that these normals intersect on the parabola. Right? So say AB are special points. What's special about these points? The normal at A and that at B intersect on the parabola at C. A normal drawn at T1, a normal drawn at T2, they intersect again on the parabola itself. Then they are special points. It will not happen for every set of 2 points on the parabola, right? For these points must be special, right? Yeah, unique. Unique in the sense special. There would be many sets of ABs, but not like every AB will be one such pair, right? There will be infinite sets of ABs which will enjoy this property, but then what must connect these ABs? In order that they could enjoy this property, what must connect them? That's the fact that we are trying to dig into, right? How should 2 points be disposed such that when normals are drawn at these points, then the two normals intersect again on the parabola itself, right? Say they intersect at a point C on the parabola, call it T3. Call it T3. Yes or no? Now, think of C as a point H comma K. Think of C as a point H comma K. Say C is a point H comma K, where what is H? H is A T3 squared, K is 2A T3. Since it's a point on the parabola, it must be of this format. A T3 squared comma 2A T3. Clear? Now, from any point in general, 3 normals could be drawn to the parabola. Right? From any point HK in general, 3 normals could be drawn to the parabola. You know what I'm saying? So, C, look upon C as a point HK, and I want to draw 3 normals to the parabola. From the point C, which happens to be a special point on the parabola, I want to draw 3 normals to the parabola. Right? So, from C, I could have drawn a normal at B. From C, I could have drawn a normal at A. And from C, I could have drawn a normal at C. How? Like this, right? At C. From C, I could have drawn a normal at C. Yes or no? This is a normal at T3. From any point on the parabola, you could have drawn a normal, let's say, at T1, a normal at T2, and a normal at that point itself. Isn't it? Yes or no? Which means T1, T2, T3, T1, T2, T3 are feet of 3 normals drawn from C. Can I say that? T1, T2, T3 are the feet of the 3 normals drawn to the parabola from C. Yes, from C, look, I draw a normal at C, I draw a normal at B, I draw a normal at A. So from the point C on the parabola, three normals could be drawn. One at the point itself, one at some point A, one at some point B. Such would be A and B, such would be A and B. Clear? Now, so HK, the coordinates of C, will satisfy this condition. This gives me what? Feet of the three normals drawn from HK to the parabola. This gives me T1, T2, T3, the feet of the three normals drawn from HK to the parabola. Yes or no? Yes, sir. Right. Where in this case, HK is special. HK is on the parabola. HK, this H and K that appear here could be anywhere, but for the case that I am imagining, HK is special. It lies on the parabola, and therefore it could be deemed as 83 squared comma 2a T3 would be H comma K, right? So T1, T2, T3 would still be roots of this, where HK becomes special as 83 squared comma 2a T3. So all these equations will still hold good. All these equations will still hold good. Which means, look at this last equation. T1, T2, T3 is K. K is 283 for such ABs. A, which gives us T1, T2 equal to 2, which gives us T1, T2 equal to 2. Yes or no? Which means, if I have 2 points on the parabola and the normals at these points intersect again on the parabola, then the product of their T's must be 2. The product of their T's must be 2. Very important property I must tell you. If I have 2 points on the parabola, and if the normals at these points again intersect on the parabola itself, then the product of the T's of these points must be 2 for a standard parabola. Write down. Yes, I will just make a formal note of it. For a standard parabola, a pair of points AB A comma B, the normals drawn to which intersect on the parabola again, then the product of their T's must be 2 for a standard parabola. What?
The converse, like if T1 and T2 is 2, then they would intersect again.
Yeah. Yes. 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 In how many normals could be drawn such that ABs? How many such ABs exist? That's a question, right? I want you to answer that question from these equations. I want you to ponder over it. All that's given is T1 into T2 is 2, and therefore T3 would be some point here, right? K could be T1, T2 is 2. I want you to be able to figure out how many such T1, T2s, how many solutions to this equation will exist, isn't it? It's about how many solutions to this equation exist. That's the whole thing. So I want you to figure out, you should think about it from the following perspective. Given T1, T2 equal to 2, how many sets of T1, T2s could be obtained given this? How many solutions in T1, T2 can exist given this? You should be able to tell me. You know what I'm saying? And I repeat his question. He's saying, all that I know is a certain point, C on the parabola, right? How many ABs exist? think about it. How many ABs exist? How many pairs of AB will exist given that from that point C, a normal drawn at A, a normal drawn at B would be such that T1 into T2 would be 2. Okay, it's about equivalently saying. So I want you to think about it yourself and tell me, given all of these conditions must hold good, all of these conditions must hold good, where T3 would be K would be 283, etc., and so on and so forth, right? You should be able to figure out how many sets of T1 T2s, how many solutions in T1 T2 will exist. The number of solutions that will exist in T1 T2 would be the number of pairs AB, such that the normals drawn at those ABs would have the product of their T's equal to 2. Put T1 T2 equal to 2, T3 equal to this, and see how many sets of T1 T2 will exist, right? You know what I'm saying, Harshit? So work out the number of solutions to this equation. See if it is unique. Okay? Right? Now, so far so good, right? So far so good. In fact, you know, this property could also have been obtained as follows. This property could also have been obtained as follows: T1 T2 equal to 2. Say I draw a normal at A, which is T1, and I draw a normal at B, which is T2. And the normals intersect at C, which is T3. Right? Now can I say T3 is the other end of the normal drawn at T2? T3 is the other end of the normal drawn at T2? Can I say that? So I could have said T3 is minus T2 minus 2 by T2. Right? T3 is also the other end of the normal drawn at T1. Isn't it? T3 is also the other end of the normal drawn at T1. So this could have been written as minus T1 minus 2 by T1. Can this all be said? Now, this I could have written as T1 minus T2. This and this. T1 minus T2 is 2 into 1 by T2 minus 1 by T1. Yes or no? So T1 minus T2 will get cancelled, and that brings us to T1 T2 equal to 2. Yes or no? So that's another way one could have obtained this. T3 0 means it's the vertex. Right? Now, for the vertex, you know, at this point, there is only one normal, which is T equal to 0, which is this line. Now, then we will not use this condition at all. Right? We will not use this condition at all. Right? Got me? Now, look, suppose there are 3 co-normal points on the parabola, right? A, B, C are 3 co-normal points. This is T1, A T1 squared, 2A T1, B, which is T2, which is A T2 squared, 2A T2, and C, which is A T3 squared, 2A T3. These are 3 co-normal points, and the normals at these points intersect at H comma K, and therefore T1, T2, T3 would be the roots of this cubic and will be commensurate with all these requirements. Right? Now, don't do that. Given 3 points, non-collinear points, how many circles could be drawn? Unique circle, right? Through these 3 points, a unique circle could be drawn, right? So let's examine the property of a circle that passes through 3 co-normal points. We wish to examine the property of a circle passing through 3 co-normal points. right? So we are seeking to deal with a circle ABC. A circle passing through three co-normal points, call them A, B and C, right? Unwanted interruption right now, but let's resume. So bringing you back to what we got started with, three co-normal points A, B, C, right? Co-normal means the normals drawn at A, B, C intersect at some point H comma K. T1, T2, T3, the roots would be the feet of the three normals at A, B, C would be the roots of this cubic, where HK is the point where the normals at ABC meet, right? I'm seeking to examine the property of a circle passing through three co-normal points A, B and C, right? Suppose the circle that passes through ABC is x square plus y squared plus 2gx plus 2fy plus c equal to 0 is the circle that passes through these 3 points. Suppose this is a circle that passes through these 3 points. Now, how do you find the intersection of this circle with the parabola? Right? If you solve this equation and this equation together, you would get xy's that lie on the parabola as well as on the circle, right? When you solve these equations, you'll get three sets of, you'll certainly get all the points of intersection between the parabola and the circle. You'll get all the xy's that lie on the parabola as well as on the circle, right? That means a point of intersection, right? Or for convenience, if a certain xy satisfies this condition, it lies on the circle, and the same xy also satisfies x equal to 80 squared, y equal to 280, it lies on the parabola also. So we are talking of those xy's that satisfy this condition, therefore they lie on the parabola, and satisfy this condition, therefore they lie on the circle. Then those xy's would be the intersection between the circle and the parabola, yes or no? Yes. Right? So in this equation, if I replace x by 80 squared and y by 280, I get the t of the intersection between the circle and the parabola. Yes or no? If in this, replace x by 80 squared, y by 280, what would I get? I'll get the t of the intersection between the circle and the parabola. Yes or no? Isn't it? So let's do that. T of the, I know there are 3 t's that are already available, t1, t2, t3 would be at least the 3 t's. There would be one more t. In general, a circle would intersect the parabola at 4 points, of which 3 are these, A, B and C. Of which 3 are these, A, B and C. Now, let me do the needful. To seek the intersection between this circle and this parabola, put x equal to 80 squared, y is 280. G 80 squared, 2f 280 plus c is 0. X square plus y squared plus 2gx plus 2fy plus c equal to 0 will give me the t of the intersection between the circle and the parabola, right? Now do you realize that you get a polynomial of degree 4 in t? This is a polynomial of degree 4 in t, yes or no? Right? How many roots will it have? 4 roots. Of which 3 are these, t1, t2, t3, because these are also points of intersection between the circle and the parabola, right? So this equation has 4 roots and we have knowledge of 3 roots, t1, t2, t3. The circle passes through these 3 points because that's the circle that we are seeking to deal with, isn't it? So this circle that we are talking of certainly passes through t1, t2, t3 and a 4th point, t4. Yes or no? This circle passes through 3 points, t1, t2, t3 and a 4th point, t4, where t1, t2, t3 are feet of 3 co-normal points. So then, realize that this is like a squared t to power 4 highest power. What is the coefficient of t cubed here? 0. Is there any t cube that you find here? No. So that is like 0 into t cubed plus some other terms equal to 0. And what are the roots of this 4th degree polynomial? T1, T2, T3 and a fourth one of which we didn't have knowledge prima facie. So the roots of this are T1, T2, T3 and T4 are the roots of this. We had knowledge of T1, T2, T3. These were three co-normal points. Now T1 plus T2 plus T3 plus T4 is 0. Minus the coefficient of the second highest power divided by the coefficient of the highest power. So this is 0. Right? But since T1, T2, T3 are three co-normal points, T1 plus T2 plus T3 is 0. Since they were co-normal points, T1 plus T2 plus T3 must also have been 0. That would mean T4 equal to 0. T1 plus T2 plus T3 is 0. If they were co-normal points, T1 plus T2 plus T3 must have been 0. But T1 plus T2 plus T3 plus T4 is also 0, which would mean T4 equal to 0. That means the circle passes through a point T4 equal to 0. But what is this T4 equal to 0? 8T4 squared to 8T4, which is actually the point 0, 0, which is actually the vertex of the parabola. Which is actually the vertex of the parabola. Vertex V of the parabola. So this leads us to an extremely vital, important idea in parabola. Write down, just formally make a note of it. If a circle is drawn through three co-normal points on a parabola, then it must pass through the vertex of the parabola. It must pass through the vertex of the parabola. No, no, of course not. Because if T1 plus T2 plus T3 is not 0, then why would T4 be 0? Say, if these are not co-normal points, then T1 plus T2 plus T3 is minus 1, say. Then T4 will become plus 1, which is not the vertex. Right? No. Doesn't mean that if a circle passes through the vertex, it must pass through three co-normal points. No. No. In fact, just to see, this was the circle x square plus y square plus 2gx plus 2fy plus c equal to 0 was the circle. To seek the intersection between the circle and the parabola, we said put x equal to 80 squared, y is 280, right? Plus c is 0. Let's organize these terms a little bit. This is like a squared t to power 4 plus 2ag plus 4a squared t squared, right? 2ag plus 4a squared t squared plus 4af t plus c is 0. Yes or no? T equal to 0 is a root of this. T equal to 0 is a root of this. We figured that out. That means if I plug in t equal to 0, which was a fourth root T4, satisfies this. So t equal to 0 is a root of this. which means C will turn out to be 0. If you plug in T equal to 0, it will cause C to be 0. Yes or no? Right? So, which means, can I just remove this portion? Now, if C is 0, this would mean a squared t to power 4 plus 2ag plus 4a squared t squared plus 4af t is 0, plugging in C equal to 0, right? Now, this could have been written as t into a squared t cubed plus 2ag plus 4a squared t plus 4af equal to 0. Yes or no? Now, this actually has 4 roots. One is t equal to 0, the other 3 are t1, t2, t3, right? This equation has 4 roots. What are the 4 roots? One is t equal to 0, which is t4, which we designated as t4. The other 3 roots are t1, t2, t3, which are the feet of the 3 conormal points. Yes or no? Which are the feet of the 3 conormal points drawn from HK to the parabola. Now, this gives me t equal to 0. Therefore, this equal to 0 must give me t1, t2, t3. Yes or no? See, this product is 0. That means either this is 0 or this is 0. This gives me t4. Therefore, this must give me t1, t2, t3. Yes or no? Right? That means a squared t cubed plus 2ag plus 4a squared t plus 4af 4af equal to 0 must have roots t1, t2, t3. Right? Now, A is not 0 in a parabola because 4a is the latest rectum, so A is not 0. So, I have the luxury of dividing by A. So, when I divide by A, I get this. This has roots t1, t2, t3, isn't it? Right now? But t1, t2, t3 are also roots of at cube plus t into 2a minus h minus k equal to 0. Right? So, that's 1. t1, t2, t3 are also roots of at cube plus t into 2a minus h minus k equal to 0. t1, t2, t3 are also roots of at cube plus t into 2a minus h minus k equal to 0. Isn't it? That means this equation and this equation have identical roots. This equation and this equation have identical roots. If two polynomials have identical roots, then their coefficients must be proportional. Must be proportional. That means a by a, coefficient of t cubed here divided by coefficient of t cubed here. That is a by a, which is 1, must be coefficient of t 4a plus 2g divided by coefficient of t here 2a minus h, constant term here 4f divided by minus k, yes or no? Right? Got me? Now, what was my intention? I was seeking a circle passing through T1, T2, T3. So for that circle, I pretended the equation of the circle to be x squared plus y squared plus 2gx plus 2fy plus c equal to 0. And trivially, we obtained c equal to 0, but g and f were still pending. Now here's our opportunity to obtain g and f of the circle, right? If I solve these two equations, this equation, then I get the value of g. If I solve this equal to this, then I get f. So the g and f, and therefore the center of the circle minus g minus f would be obtainable from these considerations. Right? See, we knew obtained for the circle. Now from this consideration we can obtain the g and f, therefore the center minus g comma minus f of the circle. Right? Makes sense to all of you? No confusion. Now while the class is on, you are not prevented from drinking water and anything non-alcoholic, and you are not prevented from eating as long as it's not human flesh. Okay, so eat and drink in a restricted sense of the word, and I told you the restriction. So don't worry, you can eat, drink, and if nature presses too hard, ring the alarm. I'll pause for a while and I'll let you take care of nature. Okay? Okay. So then some brief basic understanding of normals to a parabola, the basic property. The most common and the most useful being that if we had three co-normal points, then the centroid of the triangle formed out of three co-normal points must lie on the axis of the parabola. This, I reckon, would be the most pivotal property of co-normal points. And also the other one where I said if a circle is drawn through three co-normal points, then the circle must necessarily pass through the vertex of the parabola, right? Now, so again, in a standard parabola, say y square equal to 4ax, if there was a point P, say h comma k, then like I told you, in general, three normals could be drawn to the parabola, right? A normal at t equal to t1, that means a point A. A normal could be drawn at B, which is t equal to t2, and a normal could be drawn at C, which is at t equal to t3. Right? A normal could be drawn at A, B, C, where t1, t2, t3, like I told you, are roots of this cubic. Now, down the line when we investigate properties of polynomials, in fact very shortly, right after my digressions on parabola, I'm going to get into polynomials and quadratics in a very specific manner, where I'm going to tell you a few things. But for the time being, let me mention, and you might just want to make a passing note of it right now. Write down a polynomial with real coefficients. A polynomial that has real coefficients will, if at all, if at all, have complex roots occurring in pairs. Will, if at all, have complex roots occur in pairs. Will have complex roots occur in pairs. That is, if alpha plus I beta be a root of the polynomial, if alpha plus I beta be a root of the polynomial, then its conjugate, which is alpha minus I beta, must also be a root of the polynomial, provided the coefficients are all real numbers. Provided the coefficients are all real numbers. Which means, write down, which means the total number of complex roots of a polynomial with real coefficients, the total number of complex roots of a polynomial with real coefficients must be even, Complex roots, total number of complex roots of a polynomial with real coefficients, must be an even number, right? Now, a pertinent question that you are likely to investigate is, well, from a point hk, given a point hk, how many real normals can I draw to the parabola, right? That means how many real normals can I draw to the parabola means how many real t1, t2, t3 can I obtain from a given hk, right? That means the number of real roots of this will give me the number of real normals from hk to the parabola, isn't it? So, number of real roots of the cubic gives the number of real normals gives me the number of real normals to the parabola, right? So one possibility is, that means number of real roots means t1, t2, t3 are the roots. t1, t2, t3 are the roots of this. In this, the number of real t's will be the number of real normals, right? Now, it's possible that all the three t's are real. That will give me the general case where all normals are real normals from hk, right? So that's one possibility. t1, t2, t3 all real means 3 real normals. 3 real normals, right? Now, so this is possible, right? t1, t2 real, 2 real normals, and t3 complex. Is this possible? No. This is not possible. That means you can't have a point hk from where you can draw 2 real normals and 1 imaginary normal. No, 2 real normals is not possible, because then it leaves you with an isolated complex root. But complex roots always occur in pairs. You can't have 1 complex root for a polynomial. You will have either 0 complex roots, or 2 complex roots, or 4 complex roots, or 6 complex roots. You're confused a little bit. I told you that a polynomial can have, with real coefficients, will have only even number of complex roots. So is it possible that this polynomial has 2 real roots and 1 complex root? No. Therefore, is it possible that from a point hk I can draw only 2 normals to the parabola? That's not possible, right? I can have all 3 real normals, but 2 real normals is not possible. You can't find a point from where only 2 normals could be drawn to the parabola. That's not a possibility, ruled out. Say 2, t1, t2 complex and t3 real. That means only 1 real normal. Is that possible? Yes, that's possible. This is possible. Huh? Any point on the axis? No. Again, not always. 1 real normal is, oh, you mean from the vertex, from the point hk? Yes, yes. That's the only real normal. From the vertex of the parabola, the axis is the only real normal that could be drawn from the vertex. Yes, absolutely, absolutely. And it's perpendicular to the tangent at the vertex. Perfect. Now, it then would make sense to understand the condition for which all three roots are real. All three normals are real and distinct. I would want to know the condition for which all the three normals drawn to the parabola are real and distinct. Now this would constitute part of calculus that we will learn later on, but let me tell you two things about it. If all normals are real and distinct, HK are real and distinct, if all normals from HK are real and distinct, we must have, I will have to keep this in a black box for the time being, but when we come to details of calculus, I'll surely tell you how this came about. We must have the following two conditions. A, H must be greater than 2A. B, K square must be less than 4 by 27A into H minus 2A whole cube. H must be greater than 2A and K squared must be less than 4 by 27A into H minus 2A whole cube. This will be the condition so that all the three T's are real and distinct. All the three normals drawn from HK are real and distinct normals. H greater than 2A means, you know, points must be somewhere like this. This is 2A 0. H greater than 2A means all points to the right of x equal to 2A. All points to the right of x equal to 2A would be H greater than 2A. But there is a limitation on K also. K squared should not exceed this value, right? So for the time being, just know this condition. I promise to get back to this when I teach you the portion of calculus that will help us obtain this. But right now I want you to remember this condition. All right. In condition to have three real and distinct normals, what should be H and K? They point from where the normals are drawn to the parabola, right? Okay. Now if someone says there is a parabola, standard parabola y squared equal to 4ax. Okay. Standard parabola y squared equal to 4ax, and I'm seeking all those points H, locus of P such that two of the three normals drawn from HK, drawn from P, are mutually perpendicular. For a parabola y squared equal to 4ax, I'm trying to find the locus of P. From a point P in general, three normals could be drawn, right? I'm seeking the locus of P such that two normals are perpendicular. Out of the three normals, two are perpendicular to each other, right? Now, from P in general, a normal could be drawn at A, which is T1, at B, which is T2, say, let me make it perpendicular, almost perpendicular, or T3, or say this is perpendicular, this looks more like it. T3, a point C, such that normals PA and PC are perpendicular. We are seeking to find the locus of all points P such that out of the three normals, two normals are perpendicular to each other. Right? Locus of all such points P for a parabola y squared equal to 4ax. That's the objective. Okay. Now, T1, T2, T3 are the feet of the three normals drawn from this variable point P? Are the feet of the three normals drawn from this variable point P? Right? Therefore, T1, T2, T3 must be the roots of this cubic. T1, T2, T3 must be the roots of this cubic. Right? Where T1 plus T2 plus T3 must be 0. Summation T1 T2, that means T1 T2 plus T2 T3 plus T3 T1 must be 2A minus H by A, and T1 T2 T3, sum of the product taken all at a time is K by A. Minus 1 cubed into minus K by A, that is K by A. Is that okay? Now, if the normal at A and the normal at C are perpendicular, what's the slope of the normal at A? Minus T1. What's the slope of the normal at C? Minus T3. And if they are perpendicular, then? Right, right. If PA perpendicular to PC, it means product of their slopes must be minus 1. Right? It means T1, T3 must be minus 1. Such must be P. Such must be P. Right? Now, if you plug in T1, T3 as minus 1, what is T2? Minus K by A. T1, T3 is minus 1. So, this would give me T2 equal to minus K by A. Hey, T2 is a root of this, so must satisfy this condition. What am I seeking? I am seeking to connect H and K. To find the locus of P, I would want to connect H and K and then generalize, replace H by X and K by Y. T2 must satisfy this condition, it's a root of this cubic. So, minus K by A then must satisfy this condition. Therefore, T2, which is a root of this, right now? Which means if T2 satisfies this condition, then A into T2 cubed, T2 cubed means minus K by A whole cubed plus T, which is minus K by A into 2A minus H minus K equal to 0 must be true. That's it. Generalize this, replace H by X and K by Y. You can also divide by K because K is not 0. You can divide by K, so this will become K squared, K, etc. and so on and so forth. Replace H by X and K by Y. So divide by K if you want, then minus K squared by A squared minus 1 by A into 2A minus H minus 1 equal to 0. Right? Or I end up getting K squared equal to minus Y squared by A squared minus 1 by A 2A minus X minus 1 equal to 0. Yes or no? Replacing H by X and K by Y. Do you realize that X is a quadratic in Y? It will therefore be a parabola. X, see, X then turns out to be a quadratic in Y. Therefore, it's a parabola. It's a parabola. So, the locus of all such P's from where the tangents are mutually perpendicular is a parabola, as you've already seen. Clear? Another parabola. Hey, sometimes when they say two parabolas are equal, let me tell you what it means when they say two parabolas are equal. It means that their latest rectum is the same. Two parabolas are equal when their latest rectum is the same. That's what it means. Simple now? Now, say this is a parabola y squared equal to 4ax. Right? This is a line of slope m. This is a line of slope m. It intersects the parabola at a and b. How do you obtain a and b? When you solve this equation with this equation, you get the point of intersection between the parabola and the straight line, right? So y equal to m. This x I can write as y squared by 4a plus c. When I eliminate x from equation 1 and equation 2, it will give me a quadratic in y. One of the roots would be y of a, the other root would be y of b, y of the intersection, right? So this would give me m by 4a into y squared minus y plus c is 0, having roots ya and yb. Yes or no? Right? Sounds all right? Now, ya plus yb would be the sum of the roots of this quadratic, and that's going to be 4a by m. Meaning, any line of slope m, if you take the y of a and the y of b for this line, that's going to be 4a by m if the slope of this line is m. If the slope of this line is m, and suppose this is a and b, then y of this a plus y of this a will be also 4a by m. If you take this line of slope m, then the y of a and y of b will still be 4a by m. That means if you are seeking a set of parallel lines, then y of this plus y of this must be the same as y of this plus y of this, must be the same as y of this plus y of this. Each will be 4a by m, which will be a property for a set of lines of slope m, a set of chords of slope m, right? Now this is one such chord of slope m. This is one such chord of slope m. C could be a parameter. C could be a parameter, right? And for all such chords, needless to say and easy to imagine, that I could have drawn a normal at A. This is a normal at A. See, this is y of A. This is y of B. I could have drawn a normal at A. I could have drawn a normal at B. And the normals intersect at P, H, comma, K. I could have drawn a normal at A, a normal at B, and the normals intersect at P, which is H, comma, K, right? You know what I'm saying? Right now? Now, it's as if there is a point P, and from this point, you could have drawn a normal at A, and you could have drawn a normal at B. And, of course not. Why should the two normals be perpendicular? Yeah. So a normal at A and a normal at B from a point P, right? Now from this point, a normal could be drawn to a third point C. Yes or no? A normal is drawn at the extremity of a chord of slope m. Normals are drawn at the extremity of a chord of slope m, and the two normals intersect at P. Now from P, a third normal could be drawn. Let's say a third normal is drawn at C. A third normal is drawn from P to C. A third normal is drawn from P, HK to C. Right? Now, Let's say the y of c is yc. Right? Y of c is yc. Now interpret it as follows. Interpret it as follows. There is a point A, there is a point B, and there is a point C now. And these points A, B, C, are they co-normal points? Because normals at these points intersect at P. Yes or no? This would mean A, B, C are co-normal points. A, B, C are co-normal points. That means YA plus YB plus YC must be 0. That means YA plus YB plus YC must be 0. Right? This would mean YA plus YB we already know is 4A by M. So YC then turns out to be minus 4A by M. Now, there is a very important fact then around this. So far so good, right? Essentially, if there is a chord of slope M, please understand this fact. Nothing difficult about it, but just register it one time. If there is a chord of slope M, let's say for a standard parabola y squared equal to 4ax, then YA plus YB for any chord of slope M would always be 4a by M. 1. Then I draw a normal at one end of a chord of slope M, draw a normal at the other end of this chord, and the two normals intersect at P. But a third normal could be drawn from P. One is at A, one is at B, and the third normal is at C. So then A, B, C are rendered co-normal, and if A, B, C are rendered co-normal, T1 plus T2 plus T3 is 0. So 2A T1 plus 2A T2 plus 2A T3 is 0. Therefore Y of A plus Y of B plus Y of C is 0. Yes or no? Y plus YB is 4A by M. Therefore YC turns out to be minus 4A by M. Interesting. Which means now the point P, this is C. Can I say that this is a normal, PC is a normal? PC is a normal? Can I then say that if I had a chord of slope M like this, a chord of slope M like this, right? And I draw a normal at A and I draw a normal at B. The normals intersect at P. Right? And if I draw a third normal from P, then that will be at C, and C of this is 4A by minus 4A by M. Y of C is minus 4A by M. If a third normal is drawn, then Y of C would be 4A by minus 4A by M, right? If I take some other chord, say this was chord 1 of slope M, and if this is chord 2 of slope M, right? I draw a normal at this A prime, and I draw a normal at B prime. This is a chord of slope M, right? Then they intersect at P prime, and for P prime, I draw a third normal. Then the third normal would again be same C, which is Y equal to minus 4A by M. Yes or no? If I take a third chord and I draw a third parallel chord and I draw normals at the extremities of the chord, then the normals intersect at P double prime, and from P double prime I draw a third normal. Then it will be at the same point C, which is Y equal to minus 4A by M. Yes or no? That means from the point P, all the three normals that are drawn, are at y equal to minus 4a by m. From all the points P, the third normal must be at y equal to minus 4a by m. Yes or no? Which brings us to an important property. If I have a set of parallel chords, and if I draw normals at the extremities of these parallel chords, if I draw normals at the extremities of this parallel chords, then the third normal from the point of intersection must be at the same point C, that is y equal to minus 4a by m. Yes or no? Right? Yes or no? Which means the third normal must be along the line y equal to minus 4a by m. Yes or no? The third normal, which is this, must be along y equal to minus 4a by m. Yes or no? Collinear, and they lie on the line y equal to minus 4a by m. Perfect. All these p's would be collinear and they would lie on the normal y equal to minus 4a by m. All these p's obtained by intersection of these normals at the extremities must be collinear points and must lie on the same normal, the normal drawn at y equal to minus 4a by m. Very good. Right now? No confusion? Useful property. Bear this in mind. Okay? Some very pertinent facts about a parabola. One is, say if this is a parabola, call it y squared equal to 4ax. Okay? Say if this is just some line parallel to the axis, this is the axis of the parabola, this is line parallel to the axis. And say it intersects the parabola at P, which is 80 squared comma 280. Say this is the focus S, which is A0. This is the vertex A. This is the vertex A, which is 0, 0 in this case, for a standard parabola. Say this is the tangent drawn at P. Oh, it's a crooked one. This is a tangent drawn at P. What's the equation of the tangent at P? Yt is x plus 80 squared. Right? And it intersects the axis at T. That means put y equal to 0, then the coordinates of T would be minus 80 squared comma 0. Right? Suppose this is a normal at P. I told you that intersects the axis at G, a result which I mentioned some time back. 2a plus at squared comma 0 is the normal at P. Now one thing, for a parabola, say y squared equal to 4ax, or this is the focus S, this is the directrix x equal to a, this is the y axis, this is x plus a equal to 0, and if there is a point P x comma y, then SP is the focal radius, is the distance of the point P from the focus, is the focal radius at P, is the focal radius at P, right? Then from definition, SP must be equal to PM. From definition, SP must be PM. Now, what is PM? PM is, this is x and this is a units. So PM is x plus a. So if a point for a standard parabola has coordinates x comma y, then its distance from the focus is going to be x plus a would be its distance from the focus. S x plus a would be its distance from the focus. Now, x of P is 80 squared. So SP would be x plus a. That means 80 squared plus a would be SP. Yes or no in this case? X plus a, distance of a point x comma y from the focus S is going to be x plus a, right? So SP is x, which is 80 squared plus a. Right? Okay. What is ST? A minus 80 squared, which is a plus 80 squared. That's ST. Yes or no? Distance between S and T, a minus 80 squared. That means a plus 80 squared, right? What is SG? Same, 2a plus 80 squared minus a, which is like a plus 80 squared. Yes or no? So then we have the following things going on for us. SP is the same as SG, is the same as ST. SP is the same as SG, is the same as ST. Yes or no? Now, this is a line parallel to the axis, right? Therefore, if this angle is theta, what will this angle be? Theta, corresponding angles? Right. Now, ST is the same as SP. ST is the same as SP. ST is the same as SP. Therefore, SPT is an isosceles triangle. And therefore, if this angle is theta, this must also be theta. Because ST is the same as SP. So, isosceles triangle. So, if this is theta, this must also be theta. Yes or no? Okay. Now, this is a normal at P. This is a tangent. Normal is perpendicular to the tangent. So, if this angle is theta, what is this? 90 minus theta. If this angle is theta, what is this? 90 minus theta is this angle. Yes or no? Now, realize then the implication of this. The implication of this is this is a point P. This was a line parallel to the axis. This was a line parallel to the axis, right? That line came from the axis hitting the parabola at P. this was the normal at P. This was the focus S. And it turned out that the angle that this made with the normal alpha, which is 90 minus theta, is the angle that SP made with the normal alpha, which is 90 minus theta. Right? Yes or no? Which means the way to look at it is, interpret this is, that if this is a ray parallel to the axis of the parabola, this is an incident ray, this is an incident ray parallel to the axis of the parabola, then this alpha must be the angle of incidence. Alpha must be the angle of incidence. Right? Then the angle of reflection must be also alpha, and therefore this must be the angle of reflection, and therefore this must be the reflected ray. This must be RR, the reflected ray, because angle of incidence has to be equal to angle of reflection. So if this is the incident ray, this must be the reflected ray, or PS is the reflected ray. Bringing us to a mighty useful potent property of parabolas, that if there is a ray of light running parallel to the axis of a parabola, write down, if there is a ray of light running parallel to the axis of the parabola, if there is a ray of light running parallel to the axis of the parabola, then subsequent to reflection from the parabola, it must pass through the focus of the parabola. It must pass through the focus of the parabola. Right now, any ray of light running parallel to the axis of the parabola after reflection has to pass through the focus of the parabola. This is the property used to build paraboloid mirrors. Yes, exactly. Right. To make, when you make them paraboloid and you want this to be energy centric, then all rays of light running parallel, must pass through this. So this is a high intensity region in terms of light. Very high intensity, because all rays are converging to S. All rays parallel to the axis are converging to S, the focus. That's why it's called the focus. Right? So this is the reflection property of the parabola, commonly referred to as the reflection property of the parabola. Very useful property, I have to admit. Now, this is the tangent drawn at the vertex, This is the axis of the parabola. And this is some tangent drawn at P, 80 squared, 280 is a tangent drawn at P, say. and its equation is yt is x plus at squared is the equation of the tangent at some t. To find the intersection with the tangent at the vertex, which is the y-axis, put x equal to 0, you get this point q, put x equal to 0, y will turn out to be 80. Put x equal to 0, for this point q, x is 0, so y is 80. So what are the coordinates of q? 0, comma 80. Right? Now I join q to the focus S, A0. I join q to the focus S, A0. Right? What's the slope of QS? 80 minus 0 divided by 0 minus a, which is minus t. What's the slope of the tangent? 1 by t. The tangent at t is 1 by t, which means the slope of the tangent and slope of QS is minus 1. That means QS is perpendicular to the tangent at P, perpendicular to the tangent at P. QS is perpendicular to the tangent at P. Right? Write down. The foot of the perpendicular drawn from the focus, onto any given tangent must lie on the tangent drawn at the vertex. See, this is what I mean. This is just any tangent, right? From S, if I draw a perpendicular onto this tangent, then the foot of that perpendicular would be Q, yes or no? Because SQ is perpendicular to that tangent. So the foot Q of the perpendicular drawn from the focus onto any given tangent must lie where? Must lie on the tangent drawn at the vertex. Right? Because Q lies on the tangent drawn at the vertex. The foot of the perpendicular drawn from the focus onto any given tangent, this point Q must lie on the tangent drawn at the vertex. Right? This property would be true for parabola, ellipse, hyperbola, all of them. PEH. Parabola, ellipse, hyperbola, all of them will subscribe to this property. Right? Now, some parabola y square equal to 4ax. This is the directrix. X plus a equal to 0 is the directrix. X equal to minus a. That is right. And this is a tangent drawn at some point P. P, which is 80 squared comma 280. This is a tangent at P. P, which is some T. Right? PQ is the portion of the tangent lying between the point of tangency, which is P, and the directrix. PQ is what? Just the portion of the tangent that lies between the point of tangency P and the directrix. PQ, this segment PQ. Now I claim that if S is the focus, then PQ subtends a right angle at the focus. We'll see that. This would mean PQ subtends a right angle at the focus. PQ subtends a right angle at the focus. Means angle QSP must be 90 degrees. Let's see how. Okay. I know the equation of this line, don't I? Equation of the tangent at t is yt is x plus at squared. Right? Now, the point Q has x coordinate minus a. The x coordinate of Q would be minus a because it lies on the directrix x equal to minus a. Minus a. The y coordinate of Q can be obtained by plugging in x equal to minus a here. Put x equal to minus a. You get the y coordinate of Q, isn't it? So when you plug in x equal to minus a, you get a into t squared minus 1 divided by t is what you get. Plugging in x equal to minus a, y would be a into t squared minus 1 divided by t. That's a coordinate of Q. That's where the tangent intersects the directrix, right? Okay. Now, what's the slope of QS? y2 minus y1 by x2 minus x1. That's the slope of QS, which is a into t squared minus 1 by t divided by minus 2a, right? Minus a, y2 minus this divided by minus a, which is minus 2a, right? Which is like minus 1 by 2t into t squared minus 1. Yes or no? What's the slope of PS? 2at minus 0 divided by a into t squared minus 1, right? Which is 2t by t squared minus 1. Product of the slopes minus 1. Slope of QS, check that out, into slope of PS is minus 1. So angle QS, this must be 90 degrees. So leads us to an important property, parabola, ellipse, hyperbola. All of them, PEH, parabola, ellipse, hyperbola, all of them will subscribe to this property. The portion of the tangent lying between the point of tangency and the directrix must subtend a right angle at the focus. Must subtend a right angle at the focus. Important property. Certainly an important property. The portion of the tangent lying between the point of tangency and the directrix must subtend a right angle at the focus. Clear? Now, another property. Yet another property. Property 4. Parabola focus S, focus S, this SP is said to be the focal radius at P. SP is the focal radius at P. Suppose the parabola is y squared equal to 4ax. Then the tangent at the vertex would be x equal to 0, the y-axis. X equal to 0 is the tangent at the vertex, the y-axis in this case. S then is a0, P is 80 squared comma 280, P is 80 squared comma 280, right? Now, let me draw a circle with this focal radius being the diameter. If a circle is drawn with diameter x1 comma y1 and x2 comma y2, then x minus x1 into x minus x2 plus y minus y1 into y minus y2 equal to 0 would be the equation of the circle with diameter x1 y1 comma x2 y2, right? Okay. Circle with focal radius SP, the diameter is x minus 280 into x minus 0, y minus 80 squared, y minus a equal to 0. I'm so sorry, I'll just fix this. So sorry. X minus 80 squared into x minus a plus y minus 280 into y minus 0 equal to 0 is the circle with SP being the diameter, right? Now, if there is a circle and if there is a line, how do you know if the line is a tangent to the circle? If the point of intersection of the line, see, this is a second, two distinct points of intersection. This is a tangent where the 2 points A and B coincide, right? So a line will be a tangent to a circle if the 2 points of intersection are coincident. That's when a line is a tangent, right? If A and B are distinct and real, then it will be a chord. If the two roots of intersection are imaginary, it will not intersect the circle, right? Now I am seeking to find the intersection of the tangent at the vertex with circle drawn with focal radius as the diameter, right? I am seeking to find its intersection with tangent at the vertex. Means x equal to 0. So I would obviously put x equal to 0. Then I would get the intersection between the tangent at the vertex and the circle. If I put x equal to 0 on this, yes or no? Right? Okay. So plugging in x equal to 0, I get a squared t squared plus y minus 280 into y is 0. That will give me the y of the intersection between the circle and the tangent at the vertex, right? Which is like y squared minus 280y plus a squared t squared is 0, which means y minus 80 whole squared is 0, It gives me equal values of y. It gives me coincident points of intersection. The two values of y are 80, 80. Coincident points of intersection between the line and the circle. Yes or no? Huh? Right now? See, the discriminant of this is 0. So it will give me equal values of y. Both the values of y obtained from this quadratic in y is 80, 80. That means the circle drawn with SP as the diameter would intersect the tangent at the vertex at two coincident points. Would intersect the tangent at the vertex at two coincident points, 80, 80. That means this tangent at the vertex must be a tangent to the circle drawn with SP the diameter. Yes or no? Right? So which means if a circle is drawn with diameter SP, then the tangent at the vertex must be a tangent to this circle. The tangent at the vertex, just write down. Write down a circle drawn with a focal radius as the diameter, must touch is about tangency, must touch the tangent drawn at the vertex of the parabola, must touch the tangent drawn at the vertex of the parabola, right? Right now? So if there is any focal radius as the diameter, you draw a circle with that diameter, then that circle will always touch the tangent at the vertex of the parabola. Useful property. Okay. Then a circle drawn now with a focal chord as the diameter. This is a focal chord. That was a focal radius. This S, PQ is a focal chord. S is the focus. A circle drawn with PQ, a focal chord, as diameter must touch the directrix of the parabola. Must touch the directrix of the parabola. Now that's not difficult. See, this is a focal chord, and with PQ as the diameter, I seek to draw a circle. I claim that the directrix must be a tangent to the circle. That means the directrix must touch the circle. Right? I will just give you a small indication. See, if I draw a tangent at P and I draw a tangent at Q, then these tangents must be perpendicular to each other. Tangents at the extremities of a focal chord must be perpendicular, and that they must intersect on the directrix. With this as the diameter, this will be angle in a semicircle. Think about it, isn't it? So the tangent, the directrix must touch the circle drawn with a focal chord as the diameter. Must touch the circle drawn with focal chord PQ as the diameter. A circle, if this is drawn like this, it will touch the directrix of the parabola. A circle drawn with a focal chord PQ as the diameter will touch the directrix of the parabola, must touch the directrix of a parabola. So whatever count it was, 5, right? That's the next property. Useful property and so easy to see. Useful property and so easy to see, right? Now, one very general property of all conic sections. Have I discussed the r theta equation of a conic? No. Any conic, see, will have what? A focus, a directrix. It will have a certain eccentricity E, SP by PM is E, right? It will have a focus, a directrix, and it will have an eccentricity. It will also have an axis. The conic would look symmetric about its axis, right? And that axis would be what? The axis would be a line perpendicular to the directrix and passing through the focus will be the axis of symmetry of the conic section. A line passing through the focus but perpendicular to the directrix will be the axis of the conic section always, right? And it will have a property which is the lattice rectum, which will also be a property which will tell me, let's say, how large the parabola is, right? Lattice rectum 4a tells me how large the parabola is. We commonly talk of semi-lattice rectum, which is half the lattice rectum, designated by small l. Say this is a conic section, any conic, part of any conic section. This is the axis of the conic section. This is the axis of the conic section. This is the directrix of the conic section. The conic would be symmetric about its axis, right? Let's say E is the eccentricity of this conic. L is the semi-lattice rectum. Right? Say if S is the focus, the focus must always lie on the axis of symmetry, right? Then a line, a chord of the conic passing through the focus and perpendicular to the axis would be the lattice rectum, right? So this SQ would be semi-lattice rectum. SQ would be small l, which is semi-lattice rectum. This would be small l, this will be small l. 2l will be the lattice rectum. Small l is the semi-lattice rectum. This and this are semi-lattice rectum of the parabola, right? Now, in our earlier discussions, we designated points as x comma y. To locate any point on the conic section, we connected the x and y coordinates of those points, right? Now there is yet another way we could locate points on the conic section. Any point on the conic section could have been located as how far it's from the focus, r is its focal distance, r is its focal distance, and r, different points will subscribe to different values of r. But r is not enough, because we could have had an r like this and an r like this, giving me two different points on the conic section, isn't it? A mirror image of P will have the same value of r, right? So it's not just r. Focal radius theta is the angle that the focal radius makes with the axis. Theta is the angle that the focal radius makes with the axis, right? R is focal distance. And S and theta, angle made by the focal radius. With the axis. So r and theta will uniquely determine various points on the conic section. R and theta will uniquely determine various points on the conic section, right? Theta will have values from 0 to 2 pi. Theta can have values from 0 to 2 pi. Now, QS will be L. Semi-lattice rectum, that's a property. That will be a property given to us. L and E would be given to us. The semi-lattice rectum and E would be properties assigned to us for the parabola. I want to connect R and theta. I want to find R and theta. In earlier cases, we connected X and Y coordinates of the point P. Now I'll connect R and theta for various points on the given L and E. Right? Now, see, if there is any point on the conic section A, then AS by AR would be E. If there is any point A on the conic section, then AS divided by AR is E, the eccentricity of the conic section. That's how it's defined. That means AR would be AS by E. AR would be AS by E. Distance from the directrix would be distance from the focus divided by E. AR, the distance from the directrix, would be distance from the focus divided by E. Yes or no?
Yes, sir.
Right now? So then, if this is QS, realize that this will be L by E, because if this is L, then this distance would be L by E, by definition, right? If this is R, then this distance would be R by E, yes or no? Right? Now, let me call this ST. What is this distance? R cos theta. ST is R cos theta. TR is R by E. See, this is same as R by E. Yes or no? This is R by E, so rectangle, this is also R by E. Can I then say R cos theta plus R by E is actually L by E, this whole length, this length, L by E must be the same as this length, right? So L by E must be R cos theta plus R by E. L by E must be R cos theta plus R by E. L by R therefore must be 1 plus E cos theta multiplying by E and dividing by R. Dividing by R and multiplying by E is what? That's the connection between R and theta of any point on the conic section. L is a property, the semi-lattice rectum. E is a the conic section, eccentricity. R is the focal radius, E is the eccentricity. L and E are properties. Theta and R designate any point on the conic section. Theta could be looked upon as the polar angle of the point P. Theta could have been looked upon as the polar angle of the point P, the angle with respect to the axis of the conic section. Polar angle, right? This equation of the conic section that connects R and theta of different points is called the polar equation of the conic section. This is true for all points on the conic section, right? Very useful equation, very useful equation. Now, this equation will bring us to one of the most commonly used properties of conics. All conics, parabola, ellipse, hyperbola, all of them will subscribe to the next property, because, you know, I can give any value of E and call it a parabola, ellipse, or a hyperbola. E is 1, I'll call it a parabola. E is a value 0.6, for example, I'll call it an ellipse. E is a value 21, then I'll call it a hyperbola, right? So all parabolas subscribe to this condition. Now, say this is a conic section, part of conic section, and say this is a focal chord. PQ is a focal chord of a conic section, right? PQ is a focal chord of a conic. PQ is a focal chord of a conic. PS is R1, SQ is R2. SP equal to R1 and SQ equal to R2. These are called segments of the focal chord. These are R1 and R2 are segments of a focal chord. Any focal chord. Different for different focal chords in general. R1 and R2 are segments of a focal chord. SP and SQ are segments of a focal chord. Clear? Now, for P, R is R1. For Q, R is R2. Yes or no? Right now? For P, theta is theta. For Q, theta would be theta plus pi. For Q, theta would be theta plus pi. Yes or no? The theta for Q would be the angle that SQ makes with the axis, which would be theta plus pi. Nahin? So for Q, R would be R2 and theta would be theta plus pi. Theta would be theta plus pi. Right? Both R1 theta and R2 theta plus pi must satisfy this condition. Right? I can plug in R1, R equal to R1 and theta equal to theta. R equal to R2 and theta equal to theta plus pi. Right? So then when I do that, then I end up getting L by R1 is 1 plus E cos theta. This is from the point P because R1 theta is a point on the conic section. Right? For the point Q, R is R2 and theta is theta plus pi. Right? So L by R2 is 1 plus E cos, instead of theta you have theta plus pi for Q, the other end of the focal chord. Right? Now let me add these two. This is E cos theta, this is minus E cos theta. So when I add these two equations, I get L into 1 by R1 plus 1 by R2 is 2 for all conic sections. Or this gives me L, the semi-lattice rectum, as 2 by 1 by R1 plus 1 by R2. Yes or no? What is this? Of R1 and R2. This is the harmonic mean of the segments of a focal chord. This is the harmonic mean of the segments of a focal chord. Right? R1 and R2 are segments of a focal chord. This is the harmonic mean of the segments of a focal chord. And that's always a constant. L is a constant because it's a property. The semi-lattice rectum. L is the semi-lattice rectum, right? This is semi-lattice rectum. True for all conic sections, parabola, ellipse, hyperbola, right? If you take any focal chord, then the harmonic mean of the segments of any focal chord will be the same number and it will be equal to the semi-lattice rectum of the parabola. The lattice rectum would be double of this. Right? Very useful property. Very useful property. True for parabola, ellipse, hyperbola. All of them. Right? Sounds good? Let me look at another property before you break down. Say so this is a parabola y squared equal to 4ax. Say from a point T, tangents are drawn at P and Q. P is say 8t1 squared 2a t1. Q is t2, say 8t2 squared comma 2a t2. Then what would be the coordinates of T? Right, T is going to be 8t1 t2 8t1 plus t2 would be the coordinates of T, right? Now if S is the focus of the parabola, S is the focus of the parabola 1, I want you to check for yourself TP and TQ subtend equal angles at the focus TP subtends an angle alpha at the focus, TQ subtends an angle alpha at the focus. Both TP and TQ will subtend the same angle at the focus. You might want to examine this. Focus S is A0. 2. Using distance formula, you can check ST squared is SP into SQ. ST squared would be SP into SQ. You can check using distance formula. And from 1 and 2, from 1 and 2, see from 2 for example, ST by SP is SQ by ST, and these are included angles between the two sides. The two triangles STP and SQT must be similar, not concurrent. They are similar triangles. Why should they be concurrent? They are similar triangles. Two sides and included angle proportional. STSP, SQST. Please check for yourself. Are they not similar triangles? Right? So this would give me triangle STP similar to triangle SQT. These triangles are similar. And this lead to, if this angle is beta, this will be beta. If this is gamma, this will be gamma. Such would be the disposition of the two triangles.